panel session here. It's a panel session on the perspective of 100% renewable energy systems around the world. And not only are we doing a panel discussion and session tonight, we are also doing sort of an IT experiment because we're trying to soft link to both China and US at the same time. You can say we in Europe, we built the bridge between China and US, so that's what we'll try to do anyway. So right now we have Professor Xiliang Xiang on the line. Can you wave to us?
Yes.
Yeah,
hello.
great.
Hello, everyone.
Excellent, very good, very good. Can everybody wave to Xiliang? You can't see that, Xiliang, but we have a very good audience here waiting for your presentation as well. So, my name is Henrik Lund, and when I was a young boy at the age of 13 years, the first oil crisis hit Europe, the world, and also Denmark, where I come from. And then made a big influence of me, because ever since I have been promoting renewable energy. And as the years go on, I also said we should go for the full Monty, the full solution, 100% renewable energy system. So it's really a pleasure for me here today to moderate a planning discussion of that. We have some very good panel participants here from around the world, and I will come back to that very soon. Each panel member will make a small statement, opening statement here in the beginning, and then after that I hope we can have a very free and open debate. And I hope that you, the audience, will also contribute, so we have microphones to walk around, and we hope to have your contribution. So please prepare what you can also add to this discussion here. I'll just show one little slide here to begin with. Already this morning, Professor Christian Breyer showed some slides for a paper he and I and my colleague Kenneth Hansen did recently, where we sort of documented how the scientific contributions and publications on this topic, 100% renewable energy, is really increasing. I have added one slide to the slides you already showed this morning here, and that is the slide that you actually produced and sent to me in the very beginning, and that is the slide that also tells in which journals do we find these publications. And the reason why I show it is because I'm extremely proud and happy to say that the Energy, the journal that I edit, is among the leading forum for this discussion here. So that's why I show this diagram here. As I mentioned, I would like all of you to contribute to the discussion. That could be something about how we should design the 100% renewable energy systems. How much wind should we have? How much PV should we have? How much biomass should we include? Should we rely mostly on the hydrogen or electrofuels or the electricity storage and so on? We already heard something this morning, but also your contribution on what the technologies, what the role of them are, and how should we design the system. Of course, also contribution on how should we model it. Can we predict the future as scientists? Can we model it? What kind of information can we gain out of energy system analysis modeling? Of course, also another topic could be, we have addressed the global issue and we'll be around the world here, but even though we are around the world and look at the global issues, everything has to start in your own building and by yourself and your local community. So how should we connect what we do locally and nationally and regionally, as in Europe, US, and China, and also on the global level? That could also be one of the issues. We have some very good panelists here. We have 5 panelists, and I will introduce you one by one. And then 2 of you is not here present in the room today. We hope it'll work with the online thing that we are trying to carry out this experiment here. I will first introduce the first speaker, and this is Professor Xiliang Xiang. Professor Xiliang Xiang is with us online from China. Xi Liang is a professor in economics at the Tsinghua, very highly rated Tsinghua University in Beijing, China. He's also the director there on the Institute of Energy, Environment and Economy, and also the director of the Tsinghua MIT China Energy and Climate Project. I have visited Xi Liang in Tsinghua, and I can say for myself, I can easily see that Professor Xiang is really a highly graded and very influential energy researcher in China. And also so many years ago, not so many maybe, years ago, also served on the IPCC and was a co-author of some of the reports there. So I deeply welcome you, Xi Liang, and let's hear you opening statement. Let's give Professor Xi Liang a hand here.
Hi. And thank you very much, Henrik. So, and I'm really sorry that I cannot attend this very interesting debate so in person, and because of family issues. And so I think that this panel is really fantastic, because the topic is also really fantastic because it's about 100% electricity, 100% renewable energy system, and so it's very how to say, it's not encouraging that the voice so about 100% renewable energy system is not so strong, and we really need your Henrik, you need your leadership in the future to help us to say to thinking, and also to promote the idea and the solutions for the 100% renewable energy system. And recently, so we have conducted analysis about the 2-degree target, how China energy system to transit to achieve the 2-degree targets. So also involves the large scale the deployment of the renewable. So I would like to give a talk about this, and particularly my talk will be focused on the China's electricity sector, because I think the decarbonization and China's electricity sector is the key for achieving any ambitious climate change targets. So go next slide, please. So now, this slide and give overview of the key international pledges and national legally targets about China, how to address the climate change and promote the energy system transformation. So, and there are some targets, and also involve how to promote the renewable energy. Here we refer non-fossil fuels to renewable and nuclear. Okay. So, and now I would like to go to the next slide. Okay. So this slide shows the China's electricity consumption in the future. The next slide, please. The next slide. Yeah. No. The next slide. The third, yeah, this one. Okay. So, and this shows the future of China electricity consumption, and so this is the very recent forecasting of OTIM. So the forecasting for this electricity consumption forecasting, we have considered both the electrification of China's transportation sector, the building sector, and also the residential sector. That means because of the electrification of those sectors, China electricity should be consumption should be increased, substantially from the current level. And also we also taking into account, we also taking into account about energy efficiency initiatives will be implemented in China. So this is the future of the electricity demand. I think the electricity is also the electrification of the and special energy, the special energy use. So it's also very important part to achieve Paris 100% renewable energy system. Okay. So and so this next slide, please. So this slide shows the CO2 emissions of China for China's electricity sector to achieve the 2-degree target. So you can see we really need a very deep decline immediately after the year 2000, after the year 2020, so to safeguard the 2-degree targets. Okay. The next slide. Oh, and also this slide presents the installed capacity of the electricity generation in the future. So from this slide, you can see currently China's the coal electricity, so it's still approximately 7%. It's about 6%. 6% is more than 6%. It's no, not coal. It's in terms of the in the coal in terms of the generation capacity, coal is 6%, and still dominate the Chinese electricity generation. But in the future, after the year 2020, there will be the increased installed capacity of electricity generation will largely, primarily from the renewable, the wind, the solar, and also nuclear, and also we can see even the capital existing stock of coal electricity will be substituted, so will be by renewable and also the natural gas, and also need to introduce more CCS, so power generation sector. Now the next slide. So now this gives in terms of the electricity generation. So the previous slide about the power, the installed capacity. So this slide is about the mix of the electricity. You can see right now currently renewable and nuclear together contribute approximately 20% China's electricity generation. But you can according to the if we achieve the 2-degree targets, so by the year 2020, the contribution from the nuclear and renewable will be more than 60%, and more than 60%. So by the year 2050, so it will be more than 80%. 80%. So it's and particularly you can see renewable will play a very primary. So by 2050, renewable, the contribution of renewable for the more than 60% of the total electricity generation. And also, because of the size of the electricity consumption, renewable, and also considering the cost effective, so we also need to introduce the nuclear and also the CCS. And also we also need to introduce the natural gas electricity to accommodate the intermittency issues of the renewable supply. So this is, I think, the numbers so these numbers regard the very ambitious, but it's still a big gap. So we have 100% renewable energy system right now. So and even so to achieve such kind of decarbonization of the electricity in China, we also need to take some key measures and policy measures, technological measures and policy measures needed to be taken into place so in the future. The next slide, please. So you can see here, this slide, it will highlight the key technological and policy measures China needed to taken to achieve the decarbonization of the electricity system. So first, we needed to improve the system stability right now, and starting to improve the flexibility of the coal-fired plants. And we also need to encourage the development and deployment of flexible power plants and storage, such as natural gas power plants, and increase the capacity of storage. We also needed to enhance the interconnection of the power grids, because China is a big nation, and the renewable resources in the western part of China is more abundant compared to the eastern part of China. So we also need to encourage the development of the demand response. At the same time, we also need to address the system reliability issues, and we also need to improve the renewable forecasting. We also need to consider the integration of the renewable electricity system with other energy systems, such as the heat system. So this also, I think, the heat system is also a very key part of achieving the 100% renewable energy system. Of course, we needed to promote storage and backup units. So, and this is the primary technological measures we need to adopt it. We also need to reduce policy and the institutional reforms to enabling decarbonization. So, for example, we need to develop a complete electricity market. Right now, China's electricity market is heavily regulated. So most of the electricity tariff is determined by the government. I think this is a big issue we need to address. The second, we also need to introduce the renewable portfolio standards. Yes, I think it's very much important, particularly for achieving 100% electricity, 100% renewable electricity system. And right now, I think China is building the national emission trading system. I think it's also very important to achieve, to enable the decarbonization of the electricity. Hey, hello? Hello?
Thank you very much. It's not every word that was clear and loud, but I think thank you very much for presenting it. And it was indeed encouraging, I think, for all of us to see the diagrams, and also to see such diagrams for a big country that as China, because it's so important that you also participate in this combat of the carbon dioxide emission. So thank you very much. I think we should give a hand to
Thank you.
Stay on foot if you can, and I'll try to introduce. Sorry, I need the microphone here. I will introduce the next speaker, and the next speaker will also be online, but he's tape recorded, so we should have a more direct sound on it. The next speaker is Mark Jacobson, who's a professor in Civil and Environmental Engineering at Stanford University in California, US. He's also at that university the director of the Energy Program and co-founder of the 100% Clean Renewable Energy Movement. And Mark has been serving in several boards and committees. Among others, in 2013, he served on the Energy Efficiency and Renewable Advisory Board to the US Secretary of Energy. And he's been promoting very strongly the concept of 100% renewable energy for many years. This morning we heard from Ingo Stadler that we should sometime also involve ourselves in more popular presentations, and I can say that Mark actually already in 2013 participated in the David Letterman show, so he has already been following your advice already in this early stage. But we have the presentations from, I don't know if we have Mark online, I don't think so for various reasons, but we have his presentation online.
We have a video.
Video, exactly. Yeah. Let's give him a hand, even though we can't hear.
Hi, my name is Mark Jacobson, and I want to talk about our plans to transition the world to 100% clean renewable energy for everything. We've been developing these plans over the last 10 years, not only for cities and towns, but also states and countries, and in fact for the world as a whole. The idea behind these plans is to electrify everything and then provide that electricity with clean renewable energy. By electrify everything, I mean transportation, heating and cooling in buildings, industry. We want to make those processes electric instead of running on fossil fuels. So for example, we would use electric vehicles, some hydrogen fuel cell vehicles for long distance, heavy transport. We'd use heat pumps that run on electricity for both air conditioning and heating in buildings, including water and air heating. And for industry, we'd electrify those using existing electrical technologies for high temperatures. And we provide all the electricity with onshore and offshore wind, solar photovoltaics on rooftops and in power plants, concentrated solar power, geothermal power, existing, for the most part, hydroelectric power, and small amounts of tidal and wave power. And if we do this, we've developed plans actually for 143 countries, and including South Africa, and we find that such a transition will significantly reduce costs, create jobs, and eliminate between 4 to 9 million air pollution deaths that occur worldwide each year due to fossil fuel and biofuel combustion. And we will eliminate most of the emissions associated with global warming and provide energy security at the same time, all at a lower cost. So we think this is really important, an important transition to undertake. And there are several ways that we can get there, because the big question is, well, how can we actually transition to such a clean energy economy? Well, divestment is one important way, because there are around $2 to $5 trillion are spent each year on energy. And in order to transition energy, we need trillions and trillions of dollars of new capital for new equipment, new wind turbines, solar panels, electric vehicles. We need a lot of capital. And so we really need to transfer the funds that are used right now to prop up the fossil fuel and biofuel industries and use those funds for a clean renewable energy transition. At the same time, we also need effective policies to be put in place at national, state, local levels. In fact, there have been policies. There are 61 countries in the world that have committed to 100% renewable electricity. Now, electricity is only one portion of all energy. It's only, in fact, about 20% of all the end-use energy, but it's a start. In addition, worldwide, there are about 230 cities that have committed to 100% clean renewable energy. There are also 191 international companies, including 8 out of the 10 largest companies of the world, that have committed to 100% clean renewable energy. In the United States, there are 8 states plus Washington, D.C. and Puerto Rico have all committed to 100% clean renewable energy. They have laws on the books to do this. And this is really fantastic. And in fact, in the US, there are 130 cities and towns that have made such commitments as well. So combination of divestment, reinvestment, effective policies, and then the last prong is what individuals can do in their own homes and in their own lives. In your home, not only energy efficiency is the biggest low-hanging fruit. Beyond that, try to electrify everything. If you have a gas air heater or water heater, try to transition that to a heat pump, air heater, and water heater an air conditioner as well. For gas stoves or wood burning stoves or coal burning stoves or dung burning stoves, we want to transition those to electric induction cooktops that run on solar or wind. So there are, in fact, you can have a single cooktop that's connected to a solar panel, and that will provide your cooking, and that could save, if this is implemented worldwide, millions of air pollution deaths each year due to indoor burning of biomass and coal. And of course, electric vehicles, if you own a vehicle, of course we want to try to minimize vehicle use, so using public transport, bicycling if possible. But if you do own a vehicle, going to an electric vehicle is a good step. And of course, if you have a home, which a lot of people don't have control of their own rooftops, then try to put solar on the roof if that's an option. And batteries are now coming into play. Storage is part of the solution as well. In any case, these are just some ideas and kind of a summary of our plans. So I hope you will join us in this transition to a clean, renewable, sustainable future. Thank you very much.
Thank you very much. I don't know if you can hear us, Mark, if you are online somewhere out there, but otherwise I will say thank you very much to both Xiliang and Mark for coming with this contribution here. I realized that the IT is not working so perfectly, even though you have been working very hard to set all this up for us, and thank you for that. So now we will turn our heads to the people alive in the room for the next presentations.
Shall I try again to call to Professor Zhang?
No, I think we will leave it where we are. That will be the best for now. But that was great to hear this input for the. And from hearing this from the US and Chinese, we will turn our head now to Europe, and I will present the next speaker, even though this is a person that is very well known to all of us because it's our host, Professor Nevin Jurich. You can say no further introduction is needed, but I will give some anyway. And that is that, Nevin, you're the professor of the University of Zagreb in Croatia. I can see you have been member of various committees, among others for research infrastructure and various councils and so on. Internationally, we all know that you're very well known for being in editorial work on several international high-impact journals, as well as promoting this conference here. And then I have been knowing you since the very first Dubrovnik conference in 2002, so I can also verify that you have been building up what I will say is one of the most strongest research teams for this topic that we discuss here today, the 100% renewable energy. So please, Nevin, the floor is yours. Let's give Nevin a hand.
Thank you, Hendrik, for kind words. When in 2008, European Union has set up goals for reducing greenhouse gas emissions for 20% by 2020, I thought that was radical. But Europe did it without much problems. So we have new goals, 40% reduction by 2030, it's official. 32% renewables in energy mix by 2030 and 32.5% energy efficiency. But that actually, if you calculate just these renewables and energy efficiency, it's actually 45% reduction. And this 45% reduction is compatible with 2 degrees. But we have signed Paris Agreement and we have to now go to 1.5 degrees. And that means 55 to 60% reduction of greenhouse gas emissions by 2030. European Commission has suggested and European Parliament has voted for 55% reduction, and we will probably see in the next few months that the Council will also agree on that reduction. Also, we have an increase of price of CO2 emissions to 25 euros per ton, which is already more or less enough to kill coal. We have seen the reduction of coal last year for 18%, so that one has been solved out of 3 fossil fuels. If we look at 2050, 80% reduction of GHG is compatible with 2 degrees, while if we want to be compatible with 1.5 degree, we have to become energy climate neutral fully, which means 95% reduction of GHG. That means no fossil fuels, basically, because we also have some emissions in agriculture, which we cannot avoid so easily. Also, we will have to think about heating and transport. Gas boilers and internal combustion engine cars have 20% lifetime. So if we want to say no gas boilers and IC engine by 2050, it means we have to prohibit their sales by 2030. Some countries have already started doing that. Netherlands banned gas boilers in 2018, UK banned them after 25, Norway banned IC engines after 25, and several countries after 30. So we have to think about how to reduce the stranded costs. Otherwise, people will be buying obsolete equipment, which they will have to abandon then before the end of lifetime. This is an important thing that we want to avoid, people having stranded costs and also companies having stranded costs. So which way to go? What we heard from Christian, solar is going to be so cheap that it will be the main source of energy. I would say also wind and solar will be so cheap that they will make most of new capacity. They already make around 60% of capacity on the global level, newly built capacity. That will create quite a lot of excess of electricity in some moments, or the price of electricity will go down to relatively low. First thing that happens if you have cheap electricity, you use it for heating. What is the exergy of electricity that you cannot use for better purposes? You convert it to heat. So we have basically 3 choices which are offered how to solve heating. One is district heating with power to heat, plus heat pumps with heat storage where district heating is not feasible. Or we can go hydrogen, or we can go renewable gas, biomethane and e-methane. I will later show how this compares on transport, because in transport we have similar options, electricity, hydrogen, or e-fuels. So let's look at the services we have to satisfy. Let's say transport and electricity, which will also be used for heating. We have wind and solar energy in huge amounts, and in some hours excess. If we use it directly, it is very efficient. If we produce hydrogen instead, we lose 30% already on the hydrogen production side. And then if we power vehicles with that electricity going through hydrogen, we have only 40% efficiency instead of 80% efficiency. If we produce electricity by hydrogen, it's 45% efficiency. If we use this hydrogen to hydrogenize CO2, which we have to capture from somewhere, we lose even more, and our efficiency falls down to 15% when powering cars, or to 35% when producing electricity. So, does it make sense actually to do it? Look at how much renewable electricity we have today in the EU, 2.5 petawatt hours. We would need 24 petawatt hours to power transport using carbon capture and utilization. But if we power it directly with electricity, it's only 4.5. It is, of course, possible to go through e-methane or e-fuels, but we would actually need 7 times more primary energy to do that. So it doesn't make sense, because we want to reduce the amount of primary energy as much as possible. So that's why we go to electricity when it's feasible, and then we use hydrogen only in those places where it's not feasible, and that is in some industry and maybe for some balancing of the energy system, and for some heavy transport we're going to need carbon-based fuel because they need high energy density of fuels. And with this, I would like to end with my introductory talk. Thank you.
Thank you very much for this. And from this, you can say, being in China, US, Europe, we now turn our head to the next speaker, and that is Professor Natasha Markowska, that is professor of the Research Center of Energy of the Macedonian Academy of Science. And you have also been a member of various European program committees and a lot of things, so I know you can easily cover not only Macedonia but also Europe, but that's not why you're here, because we invited you because you actually served at the IPCC panel for quite a number of years, since 2003, as far as I have been able to look up. That's quite a number of years, so we know you have been quite influential in that and also have a lot of knowledge from there to share. So now we lift the whole thing to the United Nations level. Please welcome Natasha Markowska.
So, good evening. The views from UNFCCC Science. Many things were said today from Christian, but I would like to also to elaborate a little bit more how UNFCCC or UN looks into the energy transition and how they plan to do that. Many times mentioned today, but last year, on invitation of UNFCCC, the Intergovernmental Panel on Climate Change provided its special report on 1.5 degrees global warming, which explained how the world would look like if the temperature rise 1.5 degree compared to pre-industrial levels. And not only that, but also it developed some pathways how this can be achieved. It cited more than 6,000 research papers, so big, immense scientific literature dealing with this issue, and 91 contributions from 91 authors were taken into account to evaluate the warmer, 1.5 degrees warmer world and the pathways that limit global warming to 1.5 degrees. These pathways differ in many ways. They reflect different futures and differ in a way what kind of trade-offs and benefits with regards to other world priorities on the agenda, like sustainable development goals, poverty reduction, But all of them have a number of common features. And many times mentioned today is that by 2030 we have to halve the emissions, and by mid-century CO2 emissions have to fail to net zero. And all of the pathways includes renewables supplying 70% to 80% of electricity, and unabated coal use being largely phased out. Also, one of the common features of 1.5 degrees pathway that they depend heavily on utilization of carbon dioxide removal, and in order of 100 to 1,000 gigatons CO2 equivalent over the 21st century. But it is correctly noted in the report that CDR deployed at such a scale is unproven and in fact poses a major risk to our ability to limit global warming to 1.5 degrees. Christian mentioned today that 100 renewables energy systems for the very first time mentioned in this report. And this report indeed acknowledges the growing body of relevant scientific literature, which goes beyond the wide range of integrated assessment models projections of the share of renewables in their 1.5 and 2 degrees pathways. And also, in this report, we have updated representation of renewable energy resource potential, technology costs, and system integrations since the fifth assessment report of IPCC, which resulted in a higher deployment of renewable energy sources in many cases. But, there is a big but, none of the integrated assessment model projections identify 100 renewable energy solutions for the global energy systems as a part of cost-effective mitigation pathways. And the question is now, will the SDEWES science shed a different light of the role of 100 renewable energy systems in 1.5 degree pathways?
Thank you very much. And now we have the final presenter here. This is Professor Christian Breyer. You already presented this morning about the same topic. You're a professor at the Lund University in Finland. Before that, you were the managing director of renewable energy at the Rainer Lemmer Institute in Berlin. And I reckon you to be, because when I follow what is happening in publication and journals and new things coming up, I sort of consider you a shooting star in the 100% renewable energy science research, so that's very nice to have you here. And also you have, after we have been to China and Europe and US and even on the UN, you have promised me to cover the rest. So please welcome Christian.
Many thanks for the kind words. So I thought I had so much time today, so I will have only 2 slides, but with some bullet points. And the bullet points should be around the gaps in 100% renewable energy research. So what is really missing to get the full holistic picture? And maybe the first thing we already heard, that in the integrated assessment models there is not yet a single 100% renewable scenario. At least I have not yet found anything there. But of course, if photovoltaic costs are drastically too high or too outdated, then I'm not surprised that it's complicated to find. Okay, but now let's get started. First bullet point, all sectors have to be included if you really want to have a holistic picture. So that means power, heat, transport, industry, but of course also non-energetic fuel use in industry. This is mainly the chemical industry. And of course the new sector, I think this is mainly missing in practically all, I would call it energy system models as a contrast to the integrated assessment models, is then carbon direct removal and negative emission technologies. So that have to be fully implemented and with all different options. So we have their climate solutions there, or natural climate solutions there, but we have then also more technical approaches. It can be enhanced weathering, maybe coupled to direct air capture, the intensively discussed bioenergy CCS, with whatever perspective we have on that, but at least we need to have it in models to really investigate and find solutions for that. The industry sector in general and also the transport sector beyond the road transport needs to be more investigated. If you look into the papers, then for example international marine, international flights, they're very often missing. But there we have one of the harder to abate parts because we need dense chemical fuels, whether it's biofuels, whether it's electrofuels, synthetic fuels, however we call it, but we need a solution there. Of course, we have to better reflect the infrastructure when it comes to grids, whether we talk on power grids, heat grids, gas grids, whether we have their transmission systems, whether we have distribution systems, and of course the implications on system change with and without stranded assets. Because we can well imagine if there is no major adjustment for a natural gas grid, and suddenly we realize there is methane leakage with a huge global warming potential, then maybe within a few years of time such an infrastructure is simply stopped because we cannot accept it anymore. So these are things I think we have to go a bit deeper. And then of course we have so-called overnight scenarios. That means in 1 second in midnight we go from nothing on a greenfield approach to a fully 100% renewable system. This is very helpful to get a kind of indicative choice where we should head to. But in the very end we need transition scenarios because they help us to describe more a kind of investment lock-in. Because if we talk on technologies, we heard just before with cars, we use them 20 years, and 20 years is already a short period of time compared to coal-fired power plants. There we talk on 40, 50 years. So we can have a very long lock-in of existing investments. Of course, we could always say, okay, sorry, if society cannot take it anymore, then we have stranded assets. Of course, we know that exists, and that is a real threat. But of course, this can also cause major disruptions and of course, strong lobbying pressure against not to have it as stranded assets. So that requires then even more tough policies, and at least as scientists, we should have it on the radar screen and describe it with our models. What was already mentioned, we need a better geographic coverage in high resolution. So at least from the papers published in journals, Europe is understood the best because half of all articles are about Europe or different countries in Europe. US and Australia is understood well, I would say, but sometimes only for the power sector. I think US for all energy sectors, but still more on the power sector. Australia, if I remember right, it's only the power sector, so it goes not yet beyond. However, when it comes to regions in Africa, Latin America, Middle East, South Africa, South Asia, East Asia, whether it's Northeast, Southeast, we simply lack papers. And of course, I even remember discussions then with journals or editors in journals, is it just a new consulting piece if we have a new country which was never done before? This is of course then a question from a scientific point of view. If the model is not really new, but we have new data for a new country, is it scientific or is it consultancy? Of course, this is something we have to discuss. From my point of view, it's more scientific. It was never done before for such a country. Because if we have then the 150th paper for Europe with a small piece of change in methods, is it really something what is really novel compared to having an old method but for a country which was never investigated before? And of course, many stakeholders take it in the very end up and then discuss such results. Next point is investigation of key cost assumptions, in particular for the core technologies. So I think wind is not so much debated, but when it comes to solar photovoltaics, when it comes for batteries, electrolyzers, we should really make sure that we have really good cost assumptions in these models. Because IPCC with the integrated assessment models is a good example or a poor example. If you have completely outdated numbers in the models, we should be not surprised if the model concludes, okay, it's not relevant. So all this has to be investigated very well. And of course, we should never forget flexibility is key. We do not talk about only 100% renewables or more grid interconnection or more storage. In the end, we have, from a more abstract point of view, to talk about flexibility. And that has to be studied in all different regards. And of course, sometimes they are in competition. Very often they are complementary. But in the end, we talk on supply response. Also, that is possible. Just think on hydro dams, bioenergy. Of course, demand response. This is discussed quite a lot. But of course, it's the question where we have the most relevant, also in volume, in value, demand response. Then grids, already mentioned earlier. Of course, sector coupling is very important, and storage. But we have all those flexibility options. And I guess at least the 1 hourly resolved models are not so bad, and we can capture most of them, but we should make sure that they're all there. And of course, sector coupling has to be really better understood when it comes to flexibility, efficiency, cost. But I find it also quite interesting, the better you optimize it, the deeper you go, the less curtailment you really find. And just power to heat is a good example that it can be then later used in district heating, maybe only for 100, 200 hours a year, but it already pays off for good cases. This is then the second slide, which is then a bit more broader perspective. If you have a real good global 100% renewable energy system model running, then suddenly you come to the conclusion, what's about, to the question, there is not yet a single answer, but the research question is there. What's about international power-to-X trade? So fuels, chemicals, material refining. In most models, it's then done domestically, but if the resources are in South Morocco, the best for solar and wind on the same side on the planet, why one should not have really large-scale synthetic fuel or metal refining capacities there, as we have them today on Iceland or Norway, for the same reasons, by the way. So this should be better understood. What is a kind of a trade-off of lower supply for some regions, economic benefits in other regions? What is the impact on energy security? I guess a lot of research has to be done there. Something which is very important, and I'm very happy that Tobias is here in the room. We have a common paper on that currently under review. Material resource available research requires much more emphasis. So suddenly we have now several teams being able to do 100% renewable scenarios on the world. But in the end is the question, do we have all the lithium for all these batteries? Good question. We do not really know. So, depending on scenarios, do we have all the neodymium, dysprosium for all these electric engines or all these wind turbines? So these are questions we have to go deeper, and we have to check for all of the materials. For some of the materials, we can already give green light, seems to be okay. For other technologies, materials, at least I would say it's not yet so obvious. There are a few papers on net energy, energy return on energy in investment analysis. Of course, they're also helpful to understand the overall system efficiency. I guess we can really do more there. There's only 2-3 teams doing that on a system level. Energy system models have to cover all energy sectors, already mentioned before, fuel use plus, and I think this is important, CO2 management, and then of course also CDR, so CO2 carbon removal, and negative emission technologies. And this is important that the highly resolved 1 hourly running energy system models can do that, because then we can compare that really to the integrated assessment models, because it's not okay from a perspective of energy system models to complain integrated assessment models cannot do or reproduce this or that. in the end, energy system models have to deliver. And then we can question and call and ask why we have different results, then we can compare. So in the very end, global 100% renewable scenarios are needed for the full 21st century, because this is the range where integrated assessment models are done. And then we can really compare the energy sector scenarios of integrated assessment models to much higher resolved energy system models. I just mentioned today, we run a model with 145 regions. Integrated assessment models have 20 regions. Even that, for sure, will have some implications. And then, of course, we could combine both model types, because integrated assessment models are outstanding, great to describe the exchange of the energy system with all other sectors, in particular ecosystems all around with oceans, atmosphere, cryosphere, so all these systems. That's great. And this is, of course, an input which is needed by energy system models. However, the energy sector, from my point of view, can be modeled much, much better in energy system models. Some integrated assessment models do it with annual energy balancing. That doesn't make sense in a system with very high shares of solar and wind. Yeah, then, of course, we have to ask some questions. The question is why International Energy Agency, or IPCC, have obviously an institutional bias against 100% renewables. So obviously, it's not so super complicated, an integrated assessment model, just to have a model run with 100% renewables, but not a single one is existing. Why? It's a simple question. Maybe there is no answer, I don't know, but we should ask more. Maybe then something changes. And of course, where we are all rather weak, whether it's integrated assessment models or energy system models, how to incorporate societal aspects of all kinds in the models. So we try to build that in some constraints here, area availability there, phase in, phase out functions and different assumptions, but how to really reflect the will of society and societal constraints really well in the model, because in the end we all should have the attempt to be closer to reality, what really happens. Last but not least, how to project discount factors. So it was quite nice. I had today in the morning a slide on this Nature communication papers on 100% renewables for the power sector. Then we got a rebuttal. But you have uniform cost of capital of 7% for all countries for all years. This is nonsense. I said, okay, yeah, sure, maybe, but do you have a better method? Oh, no, we don't have a better method. Okay, they had a suggestion, but it does not make much more sense. But of course, it brings us to the inner core of the question when we describe models for several decades, how to project cost of capital. That's really important. And the very last one, we do not have too many review articles in the field, so we need more. And then we have a better understanding what we all together are doing there. Many thanks.
Very great. Good timing. Thank you very much, Christian. And I can see now that I and the rest of the panel, we have spent more than 1 hour now. So now I think it's time to open the debate for everybody in the room here. And you can come with the comments or questions or any kind of contribution as long as you stick to the topic. And because we have been so long, you have to be short. Yeah. That's not fair, but that's how life is. And we have a first contribution here from Yetzi, and then we have one back there.
I'll be very short. Dear Professor Breyer, let me respectfully disagree about the lack of research in Asia. You know, I'm co-editor-in-chief of a huge journal, and surprise, surprise, about 80 plus contributions dealing with renewable resources are from Asia. I think Hendrik has got a similar experience. Another question is to Neven. I very much appreciate your vision of EU by commanding, cancelling, which reminds me some other superpower. But have you got some forecast? What would be the percentage of shrinking E27 compared with escalating world population of India, Africa? How many % the EU will be actually in this business? Forecast for 2050.
You are not allowed to answer yet, because we will have more people coming in, and then we'll take a round afterwards. Thank you very much, Jitsi, for this couple of questions. We have a contribution down there. Yes, please say your name and affiliation first.
I'm Professor Svetlana Stejović from Faculty of Mechanical Engineering from Belgrade, from Serbia, and I would like to give a comments relating to hydro energy, because we are talking very much today about renewable energy. The target is 100% of renewable energy, but nobody mentioned hydro energy. We talk very much about wind and solar, but I would like to say that the most of megawatts we can produce by hydropower plants. And on the same time, as more we introduce wind or solar in electro-energetic system of one country, as more we need hydro energy, because wind and solar, they are mainly base energy, and it is very high degree of entropy, and you never know, it will be the wind, how strong it will be the sun or not. So we need hydro energy, we need hydro accumulation as green accumulators, where we can transfer this base and mainly cheaper energy to the more expensive energy. On the same time, I would like to pay attention that nowadays there are many ecological movements, and they are attacking on our hydro projects. We as engineers, I do believe we have to maybe establish some international committee in order to protect hydro energy, because they are talking about a negative environmental impact of renewable hydro energy. So we as engineers and designers and scientists, we believe this what we are doing is right. And we are not dealing with the marketing. We don't try to explain this to the majority of the people. When it comes on a public hearing, many strategic projects, especially in our region here, which is very rich with hydro energy, fell down. Community lost a lot of money producing designs, designing, thinking, researching, and in the end, because of environment, it fell down. But what means renewable? Renewables means mainly the biggest care about the environment. So we need, and I suggest that we establish maybe some board, some committee from here in order to protect this kind of renewable energy. Otherwise, we will lose many things. Wind or solar also couldn't be successfully introduced in an electro-energetic system of one country without hydro energy. We need accumulations. Thank you.
Thank you very much. I have to keep it a little short so everybody can. Anyone else who would like to? Yes, we have. You also. Okay, we take that down there first, and then you.
Hi.
Hello.
It's Özlem. Actually, this might be a very naive question. I was just wondering, because when we talk about energy, we always talk about like automobiles and how to provide them a sustainable way to fuel them, basically. And I was just wondering if there are projects on a larger scale, maybe to improve public transportation and the connections between the countries by train, because these things can directly be connected to the electric, how do you call it? the electricity. So then you also increase the efficiency, basically, right? So I just wonder what is the state, because I really don't know, and what is your opinion on that?
Good. Thank you. Thank you. And Molde? Is it on?
Is it on?
Yeah,
yeah, sorry. Yeah, my question is a bit triggered by a remark this morning of Professor Breyer saying, yes, we have the technology, we have the resources, why is it not happening? And then the answer was, well, because someone is earning. And I think that is not a problem. I think what is the problem, and that's why I was very glad with your presentation just, is that the changes we are facing are giant. The system changes, but it's not only the technical systems, it's also, for instance, our tax system should change completely. We are in a giant jigsaw puzzle which we should lay every time. And so I think our focus should more be on how to change this system, instead of just saying, well, we have sufficient wind and sufficient solar, etc., because we know that. The problem is how to get that into a working energy system. So that's my question.
Yeah, very good. Thank you. We have, let's take a couple of more questions as we go here. And thank you for being so short.
Very quick question. I just looked on my search engine for the word, well, the sentence, nearly 100% renewable energy systems. And I didn't find this word, while on the energy building side we have zero and nearly zero energy buildings. So the problem is, the question is, can this concept be useful in order to address, to overcome the bias that International Energy Agency and so on have in putting this theme on the agenda? Because, of course, several difficulties grow exponentially when we go toward 100%, but they could be addressed more easily at 95% penetration. So I understand well that ambitious targets are important, but I don't know if this concept could work. Thank you.
Thank you. We will take one more, and then we'll take a round here, and then we'll come back. So it will not be you, Peter, this time, but you will be first next time.
I just want to make some comment, and I like the word flexibility, but I'd like to put one question for the people, the batteries, panels, end of life. What is the impact, environmental impact? Because yes, this afternoon, I think, thinking about recycling, about the batteries, but you need the chemical industry. You need to look the huge amount of wastes that you need to deal with. It's why I think you need to have flexibility and social acceptance and separate some kind of, in Europe, North and South Europe. Realistic geographical situation. It's my opinion. And flexibility.
Thank you very much. Now on the panel we have overload in our heads with interesting comments and questions. So we will take a round now, and the rule is you can answer whatever you wish to answer. But you are not obliged, because we are so many here, then we can help one another answering all the many questions. But should we start with you, Nevin? Is that okay?
Okay, I got a direct question from Jiří. So I will start with that one. In Kyoto Protocol, Europe and other developed countries, as well as economies in transition, had got the task to develop technologies. And what we did in the last 20 years, we managed to develop really cheap technologies for energy transition. So I think we did important preparatory work for Paris Agreement that now includes India and China, and that starts next year. China is already the biggest market for solar, wind, and electric vehicles. And if you have seen the slides from Zhang Xiliang, well, you asked China. India is going to join us slightly later, because they're always a bit slower player. But because wind and solar are so cheap, it will just happen. If you look in Africa, if you walk in the bush in Africa, there is solar electricity everywhere. Tokelau is the first country which is 100% renewable on solar. So it will happen even faster in Africa, solarization, because they don't have grids, and solar is something that works off the grid. Other question I would like to answer is from Antonio. Well, nearly zero energy buildings is a concept that was a result of political negotiations. And 100% renewable energy systems is something that we are trying to push, not because we think it will be 100% tomorrow, but because we need to solve issues of intermittency, integration, social problems, etc. That is why the list of gap of research that Christian has shown is very important, and I agree with him that we have to work more on these gaps. So this is not really the same level. Here we have a policy that is established in Europe, and here we have a research problem, how to make energy systems 100% renewable. It doesn't have to happen. If you, for example, if you stop eating meat, then we can keep 5% of energy fossil, because the Earth can take that much CO2. But I think it's more probable that we are going to go 100% renewable than we are going to stop eating meat. I'm a meat eater, but vegetarians might think differently. So I pass the word now to...
I just want to add to the Carl's comment that we, in order to enable these transitions, we need to change the system. And I just want to add that we need to change our behaviors, behavioral changes, and also acceptance of what is the context of our energy systems. Till now, we had demand, supply following the demand, right? And now we have to become used to the new rule, that is supply, that is demand should follow the supply. So we have to have the overall acceptance of this fact and to learn how to behave under these conditions. This is also not just to have the technologies and potential, but also behavior in this new world.
Yeah, thanks. I would like to start with the comment that 80% of the renewable papers came from Asia. I don't disagree with that. My comment was on the 100% renewable energy system studies, and there we have a lack of papers from Asia. So that's the question, whether it's realistic or whether it's realistic to die with our civilization if we continue our pathway. So that might be realistic, but I still don't like this realistic future. But anyway, so at least it would be helpful to have there more papers with more discussion, in particular from local researchers, whether it's India, whether it's China, Japan, Indonesia, Philippines. So these are all countries where at least I get contacted from researchers. Can we do something together? Can I send a doctoral student into your team that we can investigate that? So the interest is growing fast. And I think that's very positive. When it comes to hydropower, I fully agree with your critique. So in our model we have built in, and luckily there is from researchers in the Netherlands a quite nice Nature Energy paper, I think it was last year or the year before, where they have a global mapping with all hydropower potential which is sustainable and economic. And exactly that potential we have now built in our model. The inconvenient truth is the current installed capacity can be increased by 50 to 100%, and that's it. That's not enough. So from a relative share, we can grow, and we have some regions in the world where hydropower is the all dominating today low-cost renewable source. However, we have also to take into account that new hydropower projects, they sometimes cost really more than wind energy and photovoltaics. But we have to be very careful. Our economic metric is not good, because we do discount factors, 5%, 7%, 10%, what else we apply. But now we deal with a technology which can be used for 100 years, typically with major reinvestment cycles of every 30, 40 years for roughly a quarter of the initial investments, because this is exactly the case for hydropower if one goes deeper. But that we cannot describe well in the models. That's really a problem due to the economic optimization we have there. So in the end, I would agree that sustainable potential should be used, and with hydropower we have to be very careful. So hydro dams can have really substantial greenhouse gas emissions when just forests are flooded, for example. That's not so good. And very valuable ecosystems can be also destroyed. So there are quite remarkable publications on Grand Inga in Congo, where we have several tens of gigawatts of potential, but in the end there might be 500 endemic species on risk. And then it's really challenging how to optimize such a situation. Luckily, solar energy is really low cost available there. And I'm not sure what is then a good compromise. But all in all, the economic sustainable potential is plus 50, 100% of what we use today. Public transport, I fully agree. So the more public transport we can have and the more interconnection of countries via rail-based systems, it would be perfect because they have the lowest carbon footprint. They can be based fully on electricity. That's perfect. And if we look how is a sustainable development on a city level, then of course one should have a rail-based mass transport, finally a metro system. Some countries are very good in that, others fully fail in that. So and of course it's a very expensive infrastructure. It costs once enormous amounts of infrastructure and then it can be used for many decades. And this is then also a question that some countries are able to manage that, others seems to be more complicated. But of course the more we have of that, the better it would be. How to model it best in, I'm not yet so sure. Because when it comes to the transport sector in these models, the rail segment has always a very tiny share of energy consumption, but of course it could replace substantial shares, for example, from aviation, but also from road transport. But maybe this is an additional gap really to go deeper in the transport sector, what could be really fixed there. So I fully agree. When it comes to how to change the system, I observe 3 and maybe we have now 4 waves of renewable energy deniers and opponents. Number 1 was, maybe 20 years ago, it will never work technically. I think this is now done. The second wave was, it may work technically, but economically it's outstanding nonsense. This is now also mainly done, but not yet fully, but we're on a good pathway. Then we have a slow rising wave of the third one. It may be technically possible, economically, maybe it's possible, but you will have never the raw materials, never the area, the biophysical limits are far beyond. And that we have to take very serious. I had this bullet point and we're researching on that. Do we have really the material? So PV seems to be okay, we have enough stone and sand and everything, but do we have enough lithium and other materials? We have to go deeper. Because if the feedback is no, then it's the question, okay, what other solutions, what other substitutions we can have? So this third wave we should take really serious. And then of course is the next aspect, and you have addressed that, is the societal resistance. So is it the resistance to change? Is it vested interest? Do we have the wrong systems adjusted? Because most societal systems we use since 100 to 500 to 5,000 years. So eating meat is a good example. But also other political systems. Or do we have really the power of the people, or do we have the power of the capital? This is a question we should ask ourselves. And maybe do the one or other decision at elections. But then Europe is a good example. 80% of a country think one should go for renewables. But in a representative democracy, then finally the government decides against it. So what is wrong in the system? 80% you can change every constitution, but still it does not happen. So something is severely wrong in that system, I fully agree. And this can only be fixed with pressure, massive pressure of people. And luckily we have the school kids which are now every Friday on the street. And they will be as long on the street as it's fixed, hopefully. And then it gets fixed. But it requires this pressure without any doubt. And to the very last question, of course, it should be obligatory that we have recycling systems for all batteries, because what is absolutely clear, maybe we can build lithium-ion batteries without cobalt, at least for stationary batteries we have them, in cars not yet, but we get close there, so maybe cobalt can be fixed. but lithium recycling is mandatory. Currently around 50% of the batteries are recycled, at least latest insights, but it should be mandatory by law. It's a must for all, very simple. And of course also other impacts, so that we have as low environmental impact as possible, and of course also for the others. So for PV, it's working that we have a recycling system. Wind energy should be also possible. I heard it could be improved. Okay, let's do it better. But of course this is done, because what should never, 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 ever happen again is the outstanding mass disaster what we have with nuclear. So we run for several decades a technology where we have no clue how to get it ever fixed. We have waste we cannot fix, the decommissioning takes decades. So this is an outstanding mess. This is never allowed again. And due to that, we have to fix it in the beginning before a technology is introduced. I fully agree. Sure.
I think, Nevin, you had a comment on the trains question?
Yeah, moving people to public transport, if I understood well. Well, that's of course excellent program. But we are doing that for the last 50 years, and people are buying more and more cars. If you look at light issue, we were pushing people to save light, to turn off light. I remember 40 years ago. And then we replaced incandescent bulbs with LED bulbs. And now we have reduced 5% electricity consumption. So technological solutions actually work more than voluntary reductions. You can do a huge campaign and then 5% of people will for some time reduce their consumption. And the other 90% or 95% will just continue their lives as usual. So I think that if we actually want to save the planet and the climate, we have to find also solutions for those people that don't want to listen to the advice on how to use public transport and things like that. We need to bring them technological solutions that are clean and climate proof. So in my opinion, yes, we should develop good public transport, push people to bicycles, because bicycles are good for health, make cities carless, make people walk again, sure, but this will not save the earth. We also need large-scale integration of renewables, and we have to do it very quick.
I'm not sure that we have answered all questions. I'm not sure we can answer all questions, but at least we have a reply to most of it, as far as I can see. So we have time for another round. And Peter, you're first in line, because you are cut off before.
Okay.
You'll get a microphone.
I was going to elaborate a little bit on the challenges, which before this, it's a good goal, but to achieve renewables supply to a high percentage, let it be even 100, you have serious challenges. Say, for example, if it's biomass, before biomass you have challenges for transportation, logistics, purely the fuel spent on transporting the biomass to processing sites, and of course the equipment, trucks and processing equipment and harvesting equipment and so on. So this requires a lot of fossil fuel itself, or maybe to siphon some of the renewable supply itself. Then if you go to wind and solar, the challenges are mainly equipment manufacturing, and the life cycle based footprints, water, plastics and others. I can give an example. When I was still in Manchester, there was a project called Solar Store. It was a nice device storing extra heat in a kind of a reactor based on hydration, dehydration of salts. And everything was perfect except one thing. on the life cycle basis, the strontium salts used in the reactor were very dangerous. So this is the Achilles heel of all renewables, actually.
Thank you. That's very kind. And any other comments, questions, contributions? Yes, please.
Thank you. Stanisław van Weiler from Poland. This panel is very interesting, and I have a question according to the electromobility. As Professor Deutsch said, people are buying more and more cars, and hopefully the electric cars will dominate soon. So they will be counted in millions, I think. And my question is it possible to connect them as a huge decentralized or maybe centralized storage for the electricity, some kind of a system, or I don't know how even to connect all these millions of single capacitors into one huge system grid, or it is very interesting issue for me, and I would like to get some answers. Thank you.
Thank you very much. Do we have a question down there, or maybe we have one here, and then you afterwards? In the blue shirts here first, and then the white shirt afterwards.
Okay, my name is Robert Berovic. I come from the University of Zagreb, and I have a question regarding the biomass and the role of biomass in the energy transition. So currently, biomass is mostly utilized to produce heat and electricity, but introducing of a lot of amount of solar and wind in the energy system will cover the problem of electricity production. So what about biomass in that field? Will the biomass be used, for example, to cogeneration to cover the peak demand for electricity, or it will be shifted in the other way to produce chemicals such as e-methane, biomethane, that can be utilized further? So this is my question. Thank you.
Okay, thank you very much. And we have down there, yes?
Mark Hamilton-Jones, AE Institute for Sustainable Technologies in Austria. I have a question kind of around I think we've heard this from two presenters, the principle of effectively electrify everything as being the key enabler for the 100% renewable energy systems. Does that imply that current innovations that we're seeing in, for example, solar thermal and biomass heat production are stranded assets maybe in 30, 40 years' time?
Very good. There's a whole theme to this. This is excellent. You are grouping your questions. That's excellent. You too?
Hello, this is Tobias June from the German Aerospace Center. So we heard a lot about adverse side effects of the energy transition. So basically coupling those models more to the field of industrial ecology. So the first question would be, what are the current research approaches of your institutions of coupling those energy transition scenarios and those models to the field of industrial ecology, which covers material flow analysis, input-output tables, or LCA? And another question is, then probably we will move in the field of multi-objective optimization, probably to get alternative solutions, because those models are mainly based on techno-economic data. But then we run into the question, especially with those models that have a high geographical and temporal resolution, to deal with the question of computing capacity, because sensitivity analysis with those big models is really difficult, and you need to be very careful about computation times. Do you have any idea how this will be dealt with in the future? Thank you.
Thank you very much. We can have one or two. Yes, we have one more. Please.
Thank you very much for interesting talk and debates. My name is Mohammed from Brno University of Technology. I would like to know each of your definition about renewable energy system, because if we know your mindset about this terminology, it can help us about this debate very much. Thank you very much.
Should we close it here and then take a round? I think we have so nicely grouped. Is that along the same line? Or you'll be first on the next? Is it okay? Oh, sorry, there's one. Should we, we'll add a couple of questions more then. I don't know who was first here. Yeah, you are.
Goran Krajic, University of Zagreb. I have a question for the panelists. What do you think about the future demand and how we can estimate it? Because there are so many disruptive technologies coming, for example, autonomous cars or drones or things like that, or maybe factories that will, as Natasha said, in which demand will follow production. So how this will impact the future of, or how it impacts your models, etc. So.
Great, thank you, Goran. And then one final here, and then we'll have a round, and then we'll see what time allows.
Okay, thank you. Paulo Silva from Brazil, University of Campinas. Two comments. The first one is regarding the cost. Professor Neven gives some ideas about the CO2 cost. Right now in Brazil is trying to implement a Renewable program that tax the CO2 emissions and try to increase the energy efficiency of the industry. I would like to know, maybe in Croatia and also in Finland, you have this kind of programs. Maybe in Europe you have this kind of methodology study and well determined. And the other comment is regarding the flexibility. When you mention flexibility, Professor Christian, how could you maybe introduce this concept of the social perspective of the interest of the stakeholders in the models? Maybe you have some ideas of some teams in these gaps you present. And also this morning you mentioned the possibility to obtain 100% of this matrix for renewable, and I would like to know in this in the key performance indicator how you use Exergy to try to guarantee that you can obtain this kind of percentage. Thank you so much.
Thank you very much. I think we'll close it here and take a round, but I think this was very interesting because all these questions were grouping around the biomass issue. How much biomass can we allow ourselves to use in the future? If it's still sustainable, how should we use it? And also, do we actually have stranded assets right now the way we use it now? I mean, even the question about the definition also is a little bit, do we include biomass in the definition of renewable energy systems or not? And how so that could also be interpreted there. And then also we come back a little bit here to the implementation issue, the taxes, and how to do it. That's for the panel. Should we let? Yeah, okay, we'll let Neven start. Great.
Well, I'm sorry that Mark Jacobson is not here because I disagree with him on the biomass issue, at least partially. I see his point because he wants to show that even without biomass we can do it. But biomass is a local issue. And I see that biomass will be used as something that is integrated with local agriculture, local waste treatment technologies, local industries, but I do not like the idea of transporting biomass from one continent to another to burn them in coal power plants. That does not look very sustainable to me. You have CO2 leakage and all sorts of things. When we look at where we think where my group thinks the biomass will end up, currently it is used a lot for heating, but exegetically using high temperature combustion for low temperature heating doesn't make sense. What makes sense is to use waste heat from other processes and deliver it through district heating in cities, while out of cities use heat pumps for heating. And that's a simple answer for biomass. But we will need biomass where we can't use electricity, like in chemical industry. We will need lots of inputs for chemical industry. And once we will not want to use fossil fuels anymore, or it will not be feasible, because currently chemical industry is piggybacking on cheap oil. But oil is cheap because we use it for transport and it's huge. But once we remove it from transport and electricity production, then it will become only 25% of the current use. And then it will become even more expensive than it is now. So it will be easier to replace it with biofuels as a source of chemical products. We also see biomass in biofuels, because we will need some high energy density uses like airplanes, transcontinental shipping, and maybe trucks. We also might need it for high temperature industrial processes. There will be not enough sustainable biomass in order to cover all the needs. That's why we will need electric fuels also, because what we can't electrify is at least 10 and more probably 20% of the current demand. I don't know if that satisfies Robert and Peter questions, but I see future of biomass. Definitely, but not in every country, because not every country has the potential, and I don't really see the future of biomass in huge imports of trunks coming to Denmark to be burned in coal power plant. I don't know about you, Henry.
Chips from Canada. Yeah, that's very good. Let's pass it on.
Maybe just to add to Peter. Issue about local life cycle based comparison about the technologies, and yes, in some cases you have some disadvantage of renewable based technologies in terms of life cycle, but also you have to take into account external costs. And when you have ordering of technologies, you also have to take care about the damages they do for the environment, climate, health. So this is also another issue which favorizes renewables.
First of all, many thanks for this broad variety of questions. I tried to get through and address most of them. Much for the biomass was already said. At least in our models, we make really sure that there are no energy crops. And because the sustainability of energy crops are really questionable, in particular if the last 10 or 15 years it had been on a rainforest territory. So I have really my ethical issue with that, also as a scientist. So due to that we are very strict, and when it comes in areas where it might be okay to have energy crops, then it's still the question from an energetic point of view why it should be done with such a low efficient option. The photosynthesis efficiency is 1% on the same area. Even if the area is not needed for anything else, then it should be more the question why not harvesting energy there, for example with solar photovoltaics, where we have an area efficiency which is a factor of 20 higher. And even if we convert it then to fuels or to chemicals, where I showed roughly the conversion efficiency is 50%, then the factor is still much higher. And do not forget, if we have raw biomass to convert it to chemicals and to fuels, the efficiency is typically also only 60%. So even if the area is available, I strongly doubt that it makes economically, and in particular from area efficiency, really sense. If the alternative is very low-cost electricity. However, if we have byproducts, waste and residues, that not to use is not efficient. So that, of course, has to be done. And due to that, I'm very sure these investments in biomass R&D, they are not stranded, because we will have always the use for it and the need for it. But of course we have also to be aware, if we want to have a fully sustainable society, then the biomass share might be around 5% of the total energy supply. And then of course is the question where the resources should be invested. If we have then in the very end, the 80–90% basis of energy solution which start with electricity and additional conversion processes, then of course from a specific point onward we have to question ourselves where to invest the resources. But that bioenergy research is absolutely needed, I think, is without any doubt. Solar thermal, I get always critics from the German Aerospace Center that we don't find concentrating solar thermal power plants, yes. But in the end, it's a question of cost competitiveness. So my previous career was in industry, and the CEO tells you very clearly you need a technical working solution, and it has to be cost effective. Because if your solution is technically working, but it costs too much, then your company goes bankrupt, and someone else will doing the business with another option. Very simple. So it has to be cost competitive. Solar thermal, for thermal applications, I think we have much better chances. But also there, the skepticism is really available, because we have high temperature processes. In principle, with concentrating thermal, we can do that. But then, of course, engineers telling me, okay, if you do it on the same site, then you may have an issue with the concentrators, because you may have a lot of dust. If you have it several kilometers separated, then you have to deliver hundreds of Celsius of high temperature delivered to another place. This is from the system integration also challenging. So I would not like to argue against, but we have to fix the challenges, and in the very end it has to be cost competitive. This is the hard end where we always have to end. When it comes to the biomass transport, I fully agree. I was really shocked when I noticed from Finland that it cost more money to transport from the very north of the country the biomass to the capital in Helsinki compared to get it imported from Brazil. So there is really something wrong. Because it has to be collected, it has to be brought on a rail structure, then you have to transport it with a railway system. This has to be enlarged, so some new investments, and in the very end, ship transport from Brazil seems to be lower in cost. That tells me we have to be very careful on the logistics, and it should be used more or less on site. So this is then kind of a conclusion there. So in the very end, the life cycle assessment is super important, of course. And net energy analysis, because we know there are biofuels where the energy return on energy invested is 0.8. So it's a waste of energy. That we should avoid, without any doubt. Okay, I have more answers, but maybe those who had questions directly to me, you could ask me later on, then I can give individual answers.
Thank you, because we're running a little late, and I just decided to allow myself a little contribution also on the biomass, because I think it's a very interesting, very important issue. And I believe it is and will be an ongoing discussion we need to have as scientists as we proceed. How much biomass can we allow ourselves to do when it's sustainable? Do we have stranded assets, etc.? I headed once a research project that ended in 2011, in which we, in the research project, both included life cycle assessment people and also agricultural and forest people. And from that I learned that this is a difficult issue, and there are different opinions about it. When I ask the life cycle assessment people how much biomass can we allow ourselves, what is sustainable, they come to a very little number. When I ask the forest people and the agricultural people, they could sort of more or less replace everything in Denmark by changing the crops we grow on the field. So that's where I was in that debate there. But bringing them together and having a constructive dialogue, what we concluded then, that was then back in 2011, is first of all there is a limit to the biomass we can consider sustainable, carbon neutral. And then beyond that limit, there's also biomass, but then it's not carbon neutral any longer. And we still stay within that limit when we design our 100% renewable energy futures. And that limit is, at least we conclude in 2011, so low that we need to take in hydrogen and something, and electrofuels, whatever, as also pointed out by the panel, in order to get enough to operate the transport, the aviation, the shipping, and so on in the future. That's one thing I learned. But we actually ended up with a recommendation. But the other thing I also learned, and also when we debate that, because we also debate exactly what was asked here in Denmark, if we have stranded assets when we burn the wood chips and so on, they're different biomass. We cannot just group it and discuss it as biomass. For example, in Denmark, we have a lot of biogas potential out of manure. And that does not only give a positive contribution, because right now we can replace coal, oil, and gas from that biogas. It also gives a positive contribution because the agriculture can then stop emitting methane. So that's a double positive contribution. And everybody, even the agricultural people and the life cycle assessment people, agree, of course, we should do that as a beginning. And right now in Denmark, 10% of our natural gas is actually being produced as biogas now, and we believe we have a much bigger potential. So it's a complicated discussion. I'm happy we raised it here. I'm happy with the contribution and the answers about it. I believe it will be an ongoing discussion. And this leaves me, I believe, to conclude this session. We have 1 or 2 minutes. If there anything you're burning to say as a last remark, I'm emphasizing burning to say as a last remark. No, then I think that today we should close a couple of minutes before the end, and then have a really enjoyable evening here in Dubrovnik. I thank all of you for coming and all of you for contributing. I think this have been a very important issue we are debating, and I think it will also go on in the future that we will debate that. I only have one last thing to do, and I've been looking forward to that. I want to see the panelists up here because I have some important diploma to hand over to you. And especially I've been looking forward for you, Nevin, to give you a diploma.
Okay.
There you are. There's also one for you, Natasha. Here you are. My pleasure. And one for you, Christian. I hope there will be, Peter is taking photos. It looks like award nominations. It's almost as good. Please give the panel a hand and give yourself a hand. Enjoy the evening and be ready for tomorrow's presentation at 9 o'clock. Thank you very much.
Joe, guys, we need the reception in a few minutes.
Oh, yeah.